Hi, and welcome to my talk TrustDBle towards trustable shared databases. My name is Mohammed, and this is joint work with my colleagues from the Technical University Darmstadt, Simon, Gloria, and Carsten. Maybe the first question that comes to your mind when hearing this title is, what is a trustable shared database? This is a valid question, so let me first illustrate the concept of a shared database with the help of an example, and then we will talk about what a trustable shared database really is. Assume that the consumer Alice has contracted with Bob to use his mobile network. Thereby, when Alice is traveling to a different country or a different area, she is also able to use Charlie's network to send messages or do phone calls. However, whenever she interacts with Charlie's network, Charlie records her usage in his own system or database, as you can see here. At the end of the month, Bob and Charlie exchange messages via a clearing service in order to settle user charges. This also enables Bob to create a single invoice to Alice, which also covers her charges with Charlie. As you can see, in this classical setup, every provider is maintaining his own database to record user interactions. In contrast, with the help of a shared database, both providers would be able to collaboratively maintain all occurring user interactions. This would enable Bob to directly access the database to create the single invoice with all charges of Alice. A shared database would also allow him to settle all charges of Alice in the next step with the help of a single database transaction. In this way, the concept of a shared database can facilitate and simplify settings in which multiple parties collaboratively maintain and access data. However, as you can imagine, there are also risks and challenges associated with this concept. One issue that can occur is that transactions could be executed incorrectly. This might be due to a system defect, but could also be the result of a malicious user activity. In the following example, you can see that while the first part of the transaction to settle Bob charges was executed correctly, the second part of the transaction was not, and Alice is left with a negative balance on Charlie's network. Even if we assume that the transaction was executed correctly, data manipulation can happen. That is, Charlie could alter the state of the database to incorrectly claim open charges against Alice. This means that we need a mechanism to record and, in the best case, prevent such manipulations. Last but not least is the issue of data protection. While Alice might be fine with Bob accessing her personal data, such as her birth date or address, she does definitely not want a foreign provider to access this data. Hence, it is important for a trustable database system to guarantee this level of control to Alice. A trustable shared database is able to address all of these issues based on the following three concepts. The first concept is verifiable processing, which demands that a predefined transaction logic must be executed correctly. The concept of auditable storage guarantees that all changes and accesses to the data are recorded in a tamper-proof way, so that any manipulation can be detected. Finally, the concept of data sovereignty guarantees that data ownership is preserved. That means, for example, that should Alice decide to cancel her contract with Bob, she should be able to revoke his access to her data. These concepts address the before-mentioned issues and make shared databases practical for many applications, such as in the healthcare or financial sector and many other industries. In the following, I will talk more about the first two concepts, as data sovereignty is one active area of future work. Now, after we have clarified what trustable shared databases are, you might ask, how would a database management system for such a database look like? And in fact, this is the question that we address in the second part of our paper. In our work, we present TrustDBle, a database management system for trustable shared databases that consists of two layers. In the storage layer, we build upon our previous work, which used blockchains as a tamper-proof storage. By using blockchains to store data, the storage layer provides the before-mentioned auditable storage guarantees. Thereby, we assume a permission setup in which all participants are known in before. Further, we use existing blockchain protocols such as Hyperledger Fabric or Ethereum to achieve consensus and replicate data. On top of the storage layer, TrustDBle provides standard database interfaces to allow clients to easily access the data. The database layer is also responsible for implementing further database techniques, such as sharding, to improve the overall scalability and performance of the system. One of our main contributions in the paper is the introduction of a secure execution engine to implement the concept of verifiable processing. In the following, I will talk in more detail about the main aspects of our secure execution engine and why TrustDBle relies on it to provide verifiable processing. But before I do that, let's take a step back and recap what verifiable processing means in the context of TrustDBle and what other approaches exist to implement it. As mentioned earlier, TrustDBle uses sharding to improve scalability and performance by parallelizing the execution of transactions across multiple shards, two in the example on this slide. In our previous work, we have shown that this approach works well for single-statement transactions. However, when dealing with more complex transactions that access multiple shards, we will run into new challenges. As we have seen in our previous Telco settlement transaction, which is shown here again, it might happen that part of a transaction is executed incorrectly. In untrusted setups, this might happen because of a malicious behavior of Charlie, for example. To address this challenge and to guarantee not only the atomicity of cross-shard transactions, but all asset properties, we have introduced a new secure execution engine in the database layer. Before we look at how this secure execution engine was realized in TrustDBle, let's quickly review possible techniques to achieve verifiable processing in general. One possible option to guarantee that transactions are executed correctly by all participants is to use blockchains and smart contracts. In this approach, we would implement the logic of a transaction as a smart contract, for example our settlement transaction, and run it using a standard blockchain. This approach, however, suffers from the typical blockchain limitations such as low throughput and also does not support executing transactions that span multiple shards. An alternative approach is to use so-called trusted execution environments such as Intel's SGX. These execution environments guarantee that a predefined code installed in this environment will run correctly and cannot be manipulated. At the same time, interactions with the outside world, that means untrusted code outside the TEE, are still possible. This technology could be used to build an entire execution engine that runs inside a trusted environment. However, in practice we quickly hit the capacity limits of TEEs, which are around 128 megabytes in the case of Intel's SGX technology. To address these challenges, we developed a hybrid approach which places only critical components with a small state, such as the log table of the log manager, inside the TEE. At the same time, we use blockchains to persist larger amounts of data, such as the state of transactions, and to implement additional verification protocols, as we did in our previous work. With the help of this concept, our current prototype can guarantee isolation and atomicity for cross-shard transactions. and we are currently working on covering the remaining asset properties as well. But for now, let's have a look at some initial evaluation results of our current prototype. The key question that we wanted to answer was if our approach is effective for executing cross-chart transactions. To do that, we used the small bank benchmark and executed an update-intensive workload across different charts. We executed the experiment with a different number of charts, as you can see on the x-axis, while keeping the load per chart constant. On the y-axis, you can see the throughput that we achieved with our current prototype. Due to some implementation details, we focused on a relative comparison between the different configurations. And as you can see, the experiment shows that the hybrid transaction processing approach is able to maintain the scalability of our system. In future, we will do a more detailed evaluation and, for example, study other scalability aspects and potential overheads of our hybrid transaction processing approach. Finally, let me quickly summarize what we talked about in the past few minutes. First, we have looked at some of the challenges and requirements that a trustable database management system needs to address, namely data sovereignty, auditable storage, and verifiable processing. After that, we talked about the architecture of our system, Trustable, and how it uses keys and blockchains to implement the concept of verifiable processing. During my presentation, I also mentioned some areas for future work, such as implementing the concept of data sovereignty and performing a more detailed evaluation of our system. With that, I'd like to thank you very much for listening, and I'm looking forward to your questions. Thank you.